This is Module 15, Lesson 1. This is a very short module. Each lesson is very brief. There's no math with this whatsoever. So if you're looking for a chance to get ahead, this would be a time to do so. You could probably quite easily complete all 3 of these lessons in a day or a day and a half instead of over the course of 3 days. So as you can see, we're going to be talking about reaction rates and equilibrium. So this first one is specifically about reaction rates. I should have taken equilibrium off of the first slide. We're going to talk about ways that you can affect reaction rate. It's kind of like when we were talking about ways to affect dissolving. Temperature is one of those things. If you raise the temperature, it usually increases the reaction rate. Now, the reason for this is given right here. When you increase the reaction rate, you increase the speed of the particles that are in your chemical reaction. And if they come into contact with each other more frequently and they collide with greater energy, then your reaction will happen faster. I have a video linked to the Canvas page where you got to this particular video. Then it shows you a visual image of how this works. I highly recommend that you click on it and that you watch that little video. I can't play it for you as a part of this, but you can certainly follow the link. Now, the next thing that affects reaction rate is concentration. If you increase the concentration of the reactants, it usually increases the reaction rate. Now, all these say usually because, as you've learned with chemistry, there's almost always an exception of some sort. But you can see it as, it almost always does that. So just think of it in your mind as increased concentration and increased temperature, it increases reaction rate. Same reason, if you put more stuff, think of it like having more people in an intersection, like at school, if you're walking through the hallways, the more people that you have, the more likely you are to bump into other people. And so just like that with our reactions, if the particles collide more frequently, then the reaction can take place faster. I have another video for you. It's through the same series about this. So if you'll click on the concentration link, you can see a visual of how that works. Our last one is particle size. So it works just like it did with solutions with dissolving. If you decrease the particle size, this increases the surface area. And again, it usually increases the reaction rate. So by the same token, if you increase the surface area, then you should increase the amount of contact that happens between the two reactants. So you get more frequent collisions and faster reaction. And you guessed it, there's a video for this too. If you click on the particle size link, you'll see the small short video explanation of this. Now, on to a couple of other things. Some other things to know about chemical reactions. You probably learned about catalysts in biology. Quite frequently in biology class, they were referred to as enzymes. Enzymes are things that speed up a reaction. It's the same thing in chemistry. A catalyst is something that speeds up a reaction. We're going to look at how it does that in just a minute. It lowers the energy that's needed to start the reaction. And here's an example for you. Like the digestion of proteins at body temp would require many years, but you have catalysts that are in your body. You actually even have enzymes in your saliva, so that as soon as you put food in your mouth, it goes to work on the first step of digestion. And then within your body, you have many other enzymes that assist in that process so that it doesn't take multiple years. Now, an inhibitor is something that interferes with catalysts. It basically stops them from working. I gave you an example down here you may have talked about in biology about putting lemon juice on apples. You could put it, like bananas turn brown, potatoes turn brown, apples turn brown when cut. And if you put lemon juice on them, what it does is it changes the structure of the catalyst so that it inhibits it. Now, a word to add right here is that catalysts are not part of the reaction. So we can write that right here because I know what it works like in class. If I don't write it, no one else does. Catalysts are not, let's put it this way, catalysts are not reactants or products. They're just kind of bystanders. They're there. They don't get changed. If you remember this from biology class at all, when you have catalysts like this, they will actually get used again and again and again and again. So unless you use an inhibitor, those same catalysts will continue to work because they're not used up. They're not part of the reaction themselves. here's our last little piece. We're looking at reaction diagrams. What you need to be able to do is you need to be able to interpret these. So I highly recommend taking a moment to copy this down so that you can study on it and review it and make sure that you know it for the test. This activation energy word right here, this is the energy needed to start a reaction. So I'll write that down right here. It's how much energy is needed to start it. So if you notice a couple of things, in this particular diagram right here, this one is exothermic. That means that it gives off more energy than it takes in. And we'll use a highlighter here. Look at this. If you look right here, it has this much energy right here all the way down to the bottom. This much energy is going in, but then you have from here all the way down, you have this much energy coming out. Actually, it goes down to here. I shouldn't have done the bottom of that. I got a little happy there with that. So let's make this right. From here to here. So you have a lot more, and I really just watched the whole thing. I don't feel like remaking the video. I'm looking at what I'm doing as I did this. So you actually have this much going in. I've been making too many videos at once, y'all. You have this much going in, and you have this much coming out. So you have a whole lot more coming out than you do going in. So anytime you have an exothermic reaction, you'll see like a shorter hill on the left side and a much larger hill on the right side, because this is the energy going in on the left, and this is the energy coming out over here on the right. Now, this one over here is endothermic. It's just the opposite of this one. You have from here to here, this much is going in, and then you have this much right here coming out from the top of the hill down to here. See, I did a better job this time. I'm paying more attention now. So this one takes in more than it gives off, making it endothermic. And this one's exo because the majority of the energy is exiting, it's coming out. So what I want you to look at it with these is notice that on the endothermic one right here, you are required to put in a whole lot of energy. The activation energy is this blue line. It's very large because, quite frankly, you have this much energy that's having to go into it. That's what's making it be endothermic. So much has to go in. On the exothermic one, the activation energy is right here. It's very short. Not much is required to make it happen. And then it shows the energy release being right here. I actually would have shown it going all the way to the top if it was me, simply because that makes more sense to show it all the way down. Now, the net that's coming out of it is this right here. This is what you actually get out of it in the very end. This one doesn't give off anything in the end. Since it sends out more less than it takes in, your net on this one is you're not in the energy making business over here, like you've lost it. All right, so be able to interpret the diagrams as whether or not they're exothermic or endothermic, be able to know where the activation energy is, know how to find the energy of the reactants and the energy of the products. Now, I don't have one on here. What I need to add to this is what happens when you put a catalyst in. So let's get rid of some of my scribbles here. Okay. With these reactions, if you add a catalyst, we'll do it in green. What's going to happen to either one of these is that it lowers the activation energy. So maybe this reaction now looks like this, a much smaller one. Same thing over here. You have a much smaller activation energy. It lowers it. It drops it down. So that's what it means when it says that a catalyst lowers the activation energy. It makes it so that you only need this much to start. And on this one, that's still a lot more, but it's less than what it was before. All right, so now you know it's practice time. Try this out. If you need me, catch me during office hours or send me a message.